Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 2nd, 2025, just yesterday. This paper presents a new model for monocular depth estimation that's estimating 3D depth from a single 2D image, which significantly improves performance in challenging nighttime scenes. The paper is titled, Depth Anything at Any Condition, and as we'll see, the visual results in difficult weather are really impressive. The authors tackle how these depth models often fail in poor lighting, making them more robust with a clever new training method. Also, the authors shared their full implementation on GitHub. You'll find everything you need to get started, like pre-trained models, quick inference scripts, and even the complete training and evaluation code. It's all there if you want to test it on your own images or reproduce their impressive results. Alright, and this first figure really shows the power of their new training method. They use what's called unsupervised consistency regularization, which means they teach the model to produce the same depth map even when an image is altered with blur or bad lighting. They also add a spatial distance constraint, a rule that helps the model better define object edges. You can see the result here. In these tough nighttime and noisy scenes, their model, on the far right, produces much clearer, more detailed depth maps, especially around people and cars. So this diagram really breaks down their training pipeline. It's a clever teacher-student setup. They start with a frozen, pre-trained teacher model that's already good at depth estimation. Then, they train a new student model. This student is shown images that have been intentionally distorted, made darker, blurrier, or with bad weather effects. The goal is to make the student's depth map consistent with the teacher's output on the original, clean image. This, combined with that spatial distance constraint, is what creates those sharp, robust results we saw earlier. And this training approach really pays off, as we can see in the results. This table compares their model, DepthAnything-AC, against others on tough real-world benchmarks, like New Scenes Night and Robot Car Night, plus datasets with rain, clouds, and fog. The two key metrics are absolute relative error, where lower is better, and delta 1 accuracy, which measures the percentage of correct pixels, so higher is better. Across the board, especially in the night scenes, their new model shows the best performance, confirming that their training method significantly boosts robustness in these challenging conditions. Building on those results, this table then breaks down why their method works so well. It's an ablation study, which is where you test the model by taking away different parts of the training process to see how important each one is. You can see the different components here, like the consistency loss, knowledge distillation, and that spatial distance constraint we talked about. The final row, where every component is active, shows the best scores across the board, especially on the challenging Robot Car Night benchmark. This really confirms that all these pieces working together are crucial for achieving that impressive robustness. So to wrap things up, the key takeaway is that DepthAnything-AC makes monocular depth estimation, that's estimating 3D depth from a single 2D image, far more reliable in the real world. Using that clever unsupervised training and the spatial distance constraint, it achieves excellent zero-shot performance. This means the model works incredibly well on new, challenging scenes it has never seen before, like at night or in the rain, without hurting its performance on regular images. It's a huge step forward for robust computer vision.